I will be teaching here the field theory course. So field theory is basically divided into two subparts. First part is field extension. Second part is Galois theory. I will be teaching here only the field extension part first. So field theory's application lies in many crucial areas in mathematics, like in cryptography, everywhere, etc. First of all, points I want to make that this is a beginners friendly course. This is a beginners friendly course. Second point, slow paced. That is no notes required. Textbook oriented course. So textbook is Abstract Algebra by today. Available online. So this is the main outline. So in field theory, we will gradually learn what is first field, then what is characteristic of field, then about some splitting field, existence of roots, normal extension, separable extension, day by day. You don't need to worry, relax. We will learn them slowly, day by day. Okay. So the first thing, let us start without any hesitation. So the first thing is, what is field? Definition. What is a field? A field is a commutative ring with unity such that every non-zero element multiplicative inverse. So better to write a field F in F. So that is the basic definition between a commutative ring with unity and a field. Because, example, okay, Z is not a field because 2 is no multiplicative inverse set. Obviously, there is not a field because every element should have multiplicative inverse. Not, I mean, if there is hundreds of element, then 99. Suppose 99 elements has non-zero elements has a multiplicative inverse. 98 and 1 0 0 obviously don't have any multiplicative inverse, so we are excluding 0, but one element fails to have multiplicative inverse, so that is not a field. Okay, similarly zx is not a field. Now what are fields? So you, the examples are, I think you have seen it manywhere. Q R C Q, okay, fields. Q means the set of all. Okay, I am not saying the set. I will say the ring rather. The ring of rational number, real number, complex number. This is rationals. You know already, but for the sake of clarification, I'm right. Real numbers. Because you know that every non-zero element, it is already a commutative ring with unity. Additionally, every non-zero element has its multiplicative inverse in that set. Okay. Oh, what is the smallest field? A smallest field. What is small field? There is a very trivial example. Or let me write as is that job yes. Or you can say cardinality infinity. That means infinite number of elements. So what is what are some fields with finite cardinality. The example is that ZP or Z mod PZ is somewhere written. Then P. In short, Z mod 2Z. It is only two elements are there. Z mod 3Z. All of them are filled. Sorry, 3 will not be there. So each prime P or each prime P, you take the quotient ring, that will give you a field. Okay. So, another example. Another example. If so, take any field. If F is a field and X is a then we will define a new field. It is called the field of fractions of polynomial. F round bracket X. It is defined as fx by gx, where x comma gx are polynomials and additionally gx non-zero. Otherwise, the denominator is, if the denominator is 0, then it is undefined, right? It is undefined. So that thing x by gx, that will give you a field. You can verify it is. So fx, where fx is a polynomial, it is polynomial by polynomial. Okay, simply this is polynomial divided by polynomial. So this is a field because it is commutative ring with unity. And if you take f mod g with g not equal to 0 and f not equal to 0, then the inverse, what is the inverse? G mod g by f. F is non-zero, I took, so the inverse is readily available here. All type of, okay, it is not all type of, all types. Set means all type of, all the, no need to write, but for clarification, you are the we are the first time in the field theory, so I am rewriting. Okay. Now see, if you look at this field. Suppose look at Z3 and look at R. Both are fields, but this is finite, infinite. Okay. One difference between the finite and infinite is there. I will define, don't worry. Characteristic. So let me define characteristic. You have already studied, I think. Let F be a field characteristic of F. Okay, let me write this is another form. F often denoted by char F or char F is to be the smallest integer that kills 1f. So kills 1f means in other words, smallest integer n, smallest integer n, in other words 1f equal to 0. So okay, I'm right. So what is 1f and 0f? 1f is of f and that is 0. It is the smallest. That is the main point. Okay, smallest. I have highlighted this. Is the smallest thing. Example. Okay. Uh, one thing I need to mention here. smallest positive integer. Smallest positive integer. Okay. So if no such positive integer exists, we characteristic of f to be 0. Okay. For example, characteristic of z t equal to p p equal to p plus 1f, that is 0 bar. Or alternatively, you could write this. Yes, okay, fine. And p is smallest such, and characteristic of r equal to 0, characteristic of u, that is also 0, because, and characteristic of c, that is also 0, because pair does not exist in positive integer in for which or equal to 0. That is, that we know, right? That we already know, because in real number only 0 is 0. So if you multiply some 1 with something, some non-zero entity, then that will become n equal to 0, because n into 1 f is n. So it is impossible. Okay. 3. But does there exist any? So from there, I can say that, I guess, it is not saying concretely, I can guess. I can guess characteristic of finite field. Finite field means cardinality finite. It is finite. And characteristic of infinite field, that is 0. So does there exist any infinite cardinality field whose characteristic is finite? Infinite field, or if with characteristic. Yes, obviously. The answer is affirmative. What can be the answer? Example 3. If be a field such that characteristic of f is p. Okay. I take any field. Consider that just write this. Consider fx, which is basically I defined sometimes ago fx mod gx f x gx. See, this field is infinite. Why it is infinite? Because x square x cube dot everything is there. So in short, x to the power I, where z plus belongs to f. So f is infinite because inside f there is only one family which is infinite. So f must be infinite cardinality. But characteristic of f is p is finite. What p? Less than finite, that is the main thing. Because p into fx by gx. What is this? So p into, let it is anxn an minus 1. Let p be that thing. That means if you multiply p there, that is p anxn. That is pan xn. In the numerator, everything will be multiplied by p. Now ai, okay, ai rather than write 0 a1 a n belongs to f, because in fx means the coefficients are from f. So implies p into a0 equal to p, a0 means a0 into 1 Okay. Now A0, I can take A0 outside and P inside. That is A0 P into 1. But characteristic of F is P. So P into 1 will be 0. That means A0 into 0. That means A0 into 0, 0. Similarly, other things, what are left over there? Similarly, uh, sorry, PA1 to PAN, everything is 0. So 0 and 0F are 0F and 0 are same here. I will write this, and 1F means 1 of field. So I will write 1 instead of 1F. They are same thing. Okay. Similarly, this 0. So P into Fx by Gx. That means characteristic of less than infinity. Because I took any arbitrary element, okay? Any arbitrary element, that is arbitrary. I need to write x by g belongs to f x is. Took any arbitrary element and multiplied by p, that is giving you 0. So p kills anything. So characteristic is, so it will obviously, in particular, it will obviously kill 1. Okay, I showed the more stronger version here, that although they are equivalent, if P kills every element, P will kill 1, and if P will kill 1, P will kill every element. Okay, so that is none. I checked that for you. Okay, now note that that is a note. Characteristic of F is always prime because every field, or if domain. So why field is a domain? Because 0 with a non-zero, then multiplicatively inverse will exist, then A inverse would be equal to 0. So it is a domain. Okay. Product of two elements is 0 means one have to be 0. Okay. So it is a domain. Because F is a domain and Characteristic of an integral domain is prime. So applying this fact, I can say this. Okay.